welcome to your very last video of the first chapter. I know that we are combining chapters 1 and chapters 3, but your test is going to be made up of information from both the first chapter and this third chapter. I do realize that the last section that we talked about, which was like all over dimensional analysis, is something still fresh, still new, and the stuff I'm going to introduce in this video is probably going to be very overwhelming and confusing. So again, we're going to take this slowly at your pace, so don't freak out. Okay, so what I totally forgot to do was an objective slide, so the things that I feel like you should know. Really, everything in this video is something I feel like you should know, and I'll talk about the objectives and what I think you should know by the end when we're discussing this. All right, so one of the biggest things that is really important when it comes to chemistry is how to measure and to do it with accuracy and precision. And so we did a lab, and we did the measurement lab, and there was a question on that lab that said, what is the source of error when you're measuring the same thing? And a lot of you, I told you, well, if I told student A and I told student B to measure the room, but I didn't tell you where to start, I didn't tell you where to end, I just told you to measure the room. We can all agree that we're probably going to do that in different ways because we have two different perspectives of the same room. I may be measuring the length of the room and someone else may be measuring the width of the room and not thinking any different about it. So there are different ways that you can look at measurements. And so I'm going to introduce this video by talking about accuracy and precision. So accuracy is a measure of how close a measurement is to the correct or accepted value. And precision is a measure of how close a series of measurements are to one another. So you can be accurate, but not precise. You can be precise, but not accurate. You can also be both accurate and precise, and then you can be neither. The greatest example I have for you when it comes to talking about accuracy and precision is a dartboard, and I am going to do that in class when we do our discussion. I'll draw some pictures for you to show you what I'm talking about. Because we have quite a bit to talk about in this video, and I really don't want to take up too much time on this when the next few slides are going to take a little bit. But again, and a good example to represent accuracy and precision is just looking at a dartboard. Another really important concept to talk about when we're talking about measurements is your percent error, or the accepted value of something. So an accepted value is a true or correct value based on general consensus. And so let's say I have some aluminum and I want to know the density of it. So I do an experiment to find the density of aluminum. Well, the accepted density of aluminum is 2.70 grams per centimeters cubed. That's the accepted density based off experiments that have been done over years and years of time. Now, if I were to do an experiment to find that density and I came up with 2.69 grams per centimeters cubed, my experimental value would be a little bit different than my accepted value. My experimental value as a measurement is the value that is measured during an experiment. So they're two different numbers, still pretty close to one another. So how you communicate that error or that miss in number is to find the percent error of something. And if any of you are in statistics, or if you're in pre-calc, you might do a little bit of this. You'll see, or even algebra 2, you'll see percent errors. And all it is the absolute value of the error divided by the percent value and multiplied by 100%. I do not have absolute values here. As far as percent error goes, we will do this in lab, especially next semester. So if I ask you to find the density of something and you come up and then it's not the same as the accepted value, then you'll have to find your percent error. And all you do is you take what you got minus what is you know to be true divided by what you know to be true times 100%. And that gives you your percent error. And again, I can do this in class as an example. All right, here's the big stuff of this video, significant figures. Some of you are going to go crazy over significant figures. And really, there are just a set of rules that you have to follow. Some rules are really obvious and you're gonna be like, yeah, I totally get that. And then there's gonna be some rules you're like, wait a minute. So we're gonna take it really slow. So again, we're going back to the idea of uncertainty, and uncertainty always exists in any measurement. Remember I talked about student A and student B. They can measure the room in two different ways. So uncertainty of any amount depends on the measurer, and your measuring tool and the quality of that measuring tool. Because if I said to measure the room and I gave one of you a meter stick that had no millimeter readings on it, and another one of you I gave you a meter stick with millimeter readings on it, you could go to a greater value or a more precise measurement or accurate measurement with your stick with millimeter readings compared to your stick without. Okay, so that is where significant figures comes in handy. They are they're always used to tell us the certainty of something. So significant figures in a measurement consists of all the certain digits in that measurement plus one uncertain or estimated digit. So that tells us we don't exactly know if this last digit is true. So for example, if I measure the room and I get 537.35 centimeters, the very last digit is always the uncertain digit. It's always the digit that says, well, it could be this, but it really could be something else. Everything else, all of these here, we're clear of. We know those to be true. Okay, so uncertainty, an uncertain digit just tells us, it gives us an estimate of something, but it doesn't really say the exact measurement. Okay, and I'm going to erase, well, I don't think I need to erase that. Anyway, so here's some rules you need to know, love, and live by. As far as significant figures goes, we will use significant figures for the entire year. So if I ever say you need to have the correct amount of sig figs, you probably should make sure you have your rules somewhere handy where you know how to follow them. Now, at some point, you're going to get to a point where you just know them, you're good to go. And I will admit, I may get a little lazy on looking at sig figs, but for the most part, I'll be pretty good, especially on tests and quizzes. I'll be pretty good at checking for sig figs. Really important when it comes to measurements, and we're going to be doing a lot of measuring. All right, so here are the rules I want you to know. All non-zero digits are significant. Non-zero digits, numbers 1 through 9, are all significant, meaning you always include them as a sig fig. So I said I didn't have to erase this, but it obviously looks like I'm going to have. Okay, so the next rule, all zeros that are between non-zero digits are significant. So that means like numbers like 5002. All of those numbers are significant. There are two non-zero digits in between those two zeros. Okay, so those two zeros do more than just hold a place. All right, next one. Zeros in front of all non-zero digits are never significant. Never significant. So that means if I have a number like 0.009, those zeros do nothing but hold the place. It tells you the value that you're at, which is in the thousands place. The one significant figure is the only one important in measurement. That is why it's known as a significant figure. That means there's one significant figure in this number. Those zeros, like I said, they are just placeholders. They just tell you the uncertain value. And that is why significant figures are important, because they tell you the certainty and uncertainty of a measurement. So those zeros are just placeholders. Placeholders apparently are not important. They are not significant. So that means there's only one significant figure in this number. Another rule is zeros after all non-zero digits that lack a decimal are never significant. There's so many words there. It's so much easier to just show you examples. Again, zeros after all non-zero digits that lack a decimal are never significant. So a number like 140, there are only two significant figures in here. This zero does not tell you anything. Again, it's a placeholder, but it doesn't tell you certainty of measurement. Okay? If it was 145, that would tell me the certainty of my measurement. But the zero doesn't tell me anything about that measurement, besides the fact that it's holding the place of something. Okay? I keep having to erase, and it's making me lose my, anyways. All right. Zero. Hold on, I can't see my. Okay, zeros in a number with a decimal point are significant. Zeros in a number with a decimal point are significant. So that means that a number like 627.0, how many significant figures are there? There are 4 there, okay? This number, 6270, and 627.0 are not the same. There are only 3 sig figs in this one. There are 4 significant figures here. And the biggest difference is the decimal. The decimal now tells you something. Okay, the decimal now tells you more than just a place value. It tells you more of the uncertainty. And I know significant figures, you're probably like, what? This makes 0 sense. Like, how is this not important? It's just all about the measurement, all about the certainty or uncertainty of that measurement. And I know that sounds stupid, but we're going to do some activities that will hopefully help make it more clear as to why these numbers are significant and not significant. All right, finally, in class, you are going to be doing more with significant figures than just figuring out how many are in a digit or how many are in a number. So you're going to probably be adding, subtracting, multiplying, and dividing. So how you do this? When you're adding and subtracting significant figures, so for example, if I had you add 7, and 57.25, if you're adding them, adding or subtracting, either way, you are going to just add and subtract like you would any normal problem, right? You'd pop that in your calculator. You'd add or subtract it. Then your answer should be rounded to the same number of decimal places as their measurement with the lowest number of decimals. Okay? So you're really only focusing on, you're adding them all, and then you're focusing on what's to the left of the, what's to the right of the decimal. Okay, so let me add these up real quick. All right, so I just added them up, and I got 93.95. And my rule says here, the answer should be rounded to the same number of decimal places as the measurement with the lowest number of decimal places. This number here has 1 decimal place. This number here has 2 decimal places. That means I need to round my number to 1 decimal place. That means my answer should be 93. So if it's 0.95, it would just be 94. I didn't do the rounding right. 94.0. Remember that 0 is significant. Okay? Probably not the greatest example. Should have done a little bit better one, because that's now probably a little more confusing. But I'll do some examples in class, so don't worry if you're kind of confused. Again, all you're doing with addition and subtraction is you're adding them as normal. And if you don't get the significant figures rule in calculations, you'll still get half credit if you just add them up or subtract them like normal. That's still credit. That's still something. So I'm not opposed to half credit. Now, multiplying and dividing, I think, is a little bit more easier. Multiply and divide as normal. So let's say I have 5.45 and times 0.37. Okay, so great. Okay, and I'm multiplying these numbers. So I'm just going to multiply as normal, 5.45 times 0.37, and I get 2.0165. Okay, so that's what I got. Now my next answer, my next rule is the answer should be rounded to the same number of sig figs as the measurement with the lowest number of sig figs. Okay, so if you look here, this has 3 significant figures. This one has 2 significant figures. That means my answer can only have 2 significant figures. Okay, so my answer should only be 2.0. Again, that's probably like, what? But we are going to practice this. I highly, highly recommend you look at the reading that I've provided to you. It's going to be super important. It gives you some really, really good practice problems. It even does a review lesson on density, and I really think that's a really good one. You may even see that on your test, not your quiz, but your test. If you have any questions, please ask me on Edpuzzle. You guys are really doing good at asking questions. Like I said, I know this is super confusing. It took me years to even figure out significant figures, and even now, sometimes I still get really confused. So, I guess that's not a new concept. I get confused about a lot of stuff. But anyway, ask me questions on Edpuzzle.